The Geometry of Snowflakes, a narration of symmetry and calm. Segment 1. The Foundation of Crystal Formation. Welcome to a gentle exploration of one of nature's most elegant creations. As you settle in and make yourself comfortable, we invite you to journey with us into the extraordinary world of snowflakes. This is a world of quiet geometry, of mathematical precision wrapped in nature's most delicate artistry. Throughout this experience, we'll be exploring the hidden symmetries and mathematical truths that shape these remarkable crystals. So let your breathing slow and allow your mind to drift into this peaceful realm of ice and geometry. Every snowflake begins its life as something incredibly small and humble. At the very start, it is a tiny hexagonal prism shaped by the fundamental nature of water itself. This isn't random, this isn't chance. The shape emerges inevitably from water's molecular structure, which dictates how ice crystals must arrange themselves. When water molecules bond together under the right conditions, they follow nature's blueprint, one that has been written into the very essence of their atomic structure. The six-fold symmetry of snowflakes arises directly from the hexagonal lattice of ice. This is not a coincidence or a decoration added by the winter sky. It is a fundamental consequence of how water molecules arrange themselves when they freeze. Water molecules bond in a pattern that naturally forms a six-sided structure, and this geometry becomes apparent in every snowflake that falls to Earth. In the depths of the cold atmosphere, these water molecules find their lowest energy state in a crystal with six-fold symmetry, and this mathematical preference shapes everything that follows. As the snowflake begins to grow, each of its arms develops independently from the corners of the hexagon. Imagine the crystal as having 6 points of growth, each one a corner of that original hexagonal prism. From these 6 corners, the snowflake extends outward, reaching into the cold atmosphere, gathering more water vapor and building itself with extraordinary care. Yet despite starting from identical points, no two snowflake arms grow in exactly the same way, due to the unique atmospheric conditions they encounter during their descent. The angle between water molecules mandates the hexagonal ice lattice. This is chemistry speaking. This is physics declaring what must be. The molecular bonds within water create an angle that is incompatible with any other crystal system. It will not be square. It will not be triangular. It must be six-sided. This fundamental constraint, built into the smallest possible units of water, echoes upward through the entire structure of the snowflake, from the molecular scale to the beautiful crystals you might hold in your hand. Snow crystals start as small, faceted prisms about the size of a period on a page, so tiny that they seem almost to exist between the visible and invisible worlds. Yet within this minuscule form lies the entire potential of the snowflake that might eventually descend from the clouds. This little prism is like a seed, carrying within it all the geometry and symmetry that will unfold as it grows through the atmosphere. Depending on how the conditions evolve around them, these minuscule prisms can grow into very different forms. Some become slender columns, reaching and extending upward and downward. Others flatten into thin plates, spreading their geometry across the sky. These early choices in growth patterns will echo through the entire life of the snowflake, creating pathways toward the different forms that we see falling from the winter clouds. Elaborate structures develop as crystals grow larger and travel through varied atmospheric conditions. What began as a simple hexagonal prism might become something far more complex, with branches and arms and delicate features that take your breath away. The transformation is not instantaneous. It is gradual, a slow unfolding as the crystal encounters different temperatures and humidity levels in the atmosphere above the Earth. The molecular structure of water ensures that all snowflakes, no matter how different they appear, will have 6 sides. You will never find a snowflake with 5 sides or 7 sides. The molecular geometry is strict, enforcing its 6-fold nature on every crystal that forms. This universal truth binds all snowflakes together, making them distant cousins in a family defined by the mathematics of water. Snowflakes can display 6-fold rotational symmetry, meaning they look the same every 60 degrees. Imagine standing in the center of a snowflake and rotating it by 60 degrees. You would see the same pattern appear again. Rotate again by 60 degrees, and again you see the same form. This happens 6 times around the full circle, giving snowflakes a kind of mathematical perfection that seems almost designed. This rotational symmetry is one of the most beautiful aspects of snowflake geometry, a perfect expression of order in nature. As we begin to understand these foundational principles, we see that the snowflake is not a random creation, but rather an expression of deep physical laws. The molecular structure of water creates the blueprint. The hexagonal lattice provides the framework, and from these simple beginnings emerge infinite variations, each one unique, each one beautiful. This is where our journey begins, in the understanding that beauty and mathematics are not separate, but intimately intertwined in the creation of these remarkable crystals. Segment 2. Symmetry, reflection, and perfect geometry. As we continue our gentle exploration, let us turn our attention to the many ways that symmetry reveals itself in snowflakes. Symmetry is not merely a visual property, not just something pleasing to look at. Symmetry is a profound expression of the underlying laws of physics and chemistry. It tells us something essential about the forces that shape the snowflake as it grows. Reflection symmetry allows a snowflake to look the same when flipped over 3 different axes. This is a different kind of symmetry from rotation. With reflection symmetry, imagine holding a snowflake before a mirror. The image you see reflects back perfectly, identical in every detail. And this works not just for one direction, but for 3 different axes of reflection. The snowflake has a mirror image quality built into its very structure, creating a kind of perfect bilateral beauty. Think of these 3 axes of reflection like 3 different ways you could cut a snowflake in half and see that each half mirrors the other. This 3-fold reflection, combined with the 6-fold rotational symmetry, creates a crystal form that is mathematically complete and elegant. These are the patterns that the snowflake must follow, not because it chooses to, but because they emerge inevitably from the way ice crystals grow. The shape of a snowflake depends on the temperature and humidity as it falls through the atmosphere. These 2 variables are like the climate in which the snowflake develops, like the environment in which a tree grows. Different conditions produce different forms. the snowflake is not static in its growth. Rather, it is responsive to its surroundings, changing its growth pattern as conditions change around it. At temperatures around -22 degrees Celsius, snowflakes often form plate-like or columnar shapes. This specific temperature window creates conditions where certain growth patterns are favored over others. At this particular coldness, the water molecules find it advantageous to grow in certain directions, creating the flat, hexagonal plates or the tall, thin columns that characterize snowflakes at this temperature range. Above saturation, snowflakes grow more lacy and ornate, becoming intricate and delicate. Below saturation, they are more compact and simple. When there is abundant water vapor available, the crystal can afford to grow in complex directions, creating branches and sidearms and elaborate features. When water vapor is scarce, the crystal must grow more conservatively, creating simpler, more compact forms. It is as if the snowflake is making choices about how elaborate it can become based on the resources available to it. Complex patterns like side planes, bullet rosettes, and planar types arise from the changing conditions that the snowflake encounters during its descent. Each of these forms represents a different path the snowflake took as it fell through varying atmospheric layers. A snowflake that passes through a warm layer, then a cold layer, then a humid layer, creates a record of these transitions in its very structure. The snowflake is like a history book written in ice. If a snowflake starts as a column and then enters a region of the atmosphere where plate-like conditions dominate, capped columns form. These are among the most exotic of snowflakes, with two flat plates that have formed on either end of what was originally a columnar crystal. These caps represent a moment when the snowflake's environment changed, when it transitioned from one growth regime to another. The result is a form that tells the story of that transition, written in the crystal structure. Plates can be simple hexagons, stellar in appearance with extended branches, or sectored with prominent ridges. A simple hexagonal plate is like the basic canvas, the simplest expression of the six-fold geometry. A stellar plate sprouts elaborate star-like branches extending in all directions with delicate arms. A sectored plate has visible ridges and divisions like a geometric design drawn by nature's hand. Occasionally, snowflakes form rare triangular crystals with only 3 sides. These are exceptions to the rule, anomalies that seem to defy the normal six-fold geometry. Yet even these triangles are related to the hexagon, emerging from specific conditions that cause the growth to favor 3-fold symmetry instead of 6-fold. They remind us that nature, while governed by rules, sometimes creates exceptions that are beautiful precisely because they are rare. As we contemplate these various forms and symmetries, we begin to see that the snowflake is not a fixed thing, but rather a process, a record of a journey through the sky. Each snowflake is unique, not because the rules are arbitrary, but because the exact conditions it encounters are unique. No two snowflakes have experienced the exact same temperature profile, the exact same humidity, the exact same journey downward. This is why they are all different, yet all share the same fundamental six-fold geometry. This is nature's way of combining order with infinite variety. Segment 3. The Dance of Branching and Faceting. Let us now explore one of the most fascinating aspects of snowflake formation, the dynamic interplay between two competing forces that shape the crystal as it grows. These forces are faceting and branching, and their dance together creates the extraordinary variety of snowflake forms we observe. Faceting is a stabilizing process that forms flat surfaces and simple shapes. When conditions favor faceting, the snowflake grows slowly, deliberately, creating smooth, flat faces on its surface. This is like watching a patient sculptor carefully carve a block of stone, creating clean surfaces and orderly geometry. Faceting creates the simple prism-like crystals that form when humidity is low and growth is slow. In these conditions, the water molecules have time to arrange themselves in orderly patterns, creating a crystal with regular faces and quiet symmetry. Simple prism-like crystals form when humidity is low and growth is slow. Imagine a snowflake falling through very dry air, moving through layers of the atmosphere where water vapor is scarce. The crystal can only grow as fast as it can gather water molecules from its environment. This slow, patient growth favors the formation of simple, regular shapes. The crystal becomes a modest prism, elegant in its simplicity, a quiet expression of hexagonal geometry. Branching, by contrast, is an unstable process that creates complex structures. When conditions favor branching, the snowflake grows rapidly, extending outward in multiple directions, creating intricate structures with arms and dendrites and elaborate features. Branching happens when there is abundant water vapor and conditions that favor rapid growth. The crystal extends outward eagerly, like a tree reaching its branches towards the sky, creating delicate arms that spread in all directions. Higher humidity yields faster growth and more complex structures. When the atmosphere around the snowflake is rich with water vapor, the crystal grows quickly. This rapid growth creates instability at the edges of the crystal, causing small perturbations to amplify into full branches. The result is a snowflake with elaborate structure, with arms reaching outward, with intricate patterns that seem almost impossibly delicate. The interplay of faceting and branching shapes snowflakes. These two forces are in constant dialogue as the crystal falls through the atmosphere. Now faceting dominates, creating clean surfaces. Then branching takes over, creating elaborate arms. The snowflake grows in response to changing conditions, shifting between these two modes of growth. The final form of the snowflake is a record of these transitions, a visible representation of the atmospheric journey the crystal has taken. Smaller crystals are generally simpler, larger ones are more complex. There is a relationship between size and intricacy in snowflakes. A crystal that has had a short journey through the atmosphere, or one that has encountered conditions that suppressed growth, remains relatively small and simple. A crystal that has had a long journey through varied conditions, that has encountered periods of rapid branching growth, becomes large and elaborate. Size and complexity are generally correlated, though there are exceptions. Snowflakes experience changing temperatures and humidity as they fall from the clouds toward the earth. The atmosphere through which a snowflake falls is not uniform. There are layers of warmer and cooler air, regions of greater and lesser humidity. As the snowflake descends, it passes through all of these layers, experiencing a constantly changing environment. Each change in environment alters the crystal's growth pattern, adding another line to the snowflake's biography. Each change in environment alters the crystal's growth pattern. Imagine the snowflake as having a memory of every atmospheric layer it has passed through. Each temperature shift, each humidity change is recorded in the crystal structure. The record is written in the shape of the crystal, in the distribution of branches, in the density of detail. An experienced meteorologist might look at a snowflake and read its history, understanding where it fell and what conditions it encountered. The knife-edge instability is a third major force in snowflake formation, one that works alongside faceting and branching to determine the final form. This is a more subtle process, one that affects the edges of growing crystals. The knife-edge instability causes the edges of a growing snowflake to become unstable, causing small ripples to form. These ripples can then grow into the delicate features and intricate patterns that we admire in snowflakes. Without this knife-edge instability, snowflakes would be smaller and blockier, lacking the elaborate features and delicate detail that make them so beautiful. This instability is actually a necessity, a requirement for the beautiful complexity we observe. It is the turbulence at the edge, the chaos that creates order. The snowflake needs this instability to develop its intricate patterns. Without it, snowflakes would be simpler, more regular, less beautiful. As we contemplate these three forces, we begin to understand that snowflake formation is a complex dance, a dynamic process where multiple forces interact to create the final form. No single force dominates completely. Instead, they work in concert, each one influencing the others, creating a symphony of growth and change. The snowflake is the result of this dance, a physical manifestation of the interplay between stability and instability, between order and complexity. Segment 4. The molecular lattice and crystal faces. Now let us turn our attention to the most fundamental level of snowflake structure, the molecular lattice that underlies all snowflake formation. To truly understand the snowflake, we must understand how water molecules arrange themselves when they freeze, and how this arrangement at the molecular scale determines the structure at every larger scale. The molecular lattice determines which surfaces grow slowly and which grow rapidly. Not all surfaces of a crystal grow at the same rate. The lattice structure of ice creates preferred directions for growth, directions where water molecules naturally align and attach more easily. Some faces of the crystal have a surface structure that makes it easier for new molecules to attach. Other faces present more resistance. This difference in growth rates is fundamental to understanding crystal geometry. Faceting reveals the geometry of the water molecule in large crystals. When you look at a large snowflake and see its flat faces, you are seeing the direct result of the molecular structure of water. The hexagonal shape, the angles between faces, the relationships between different crystal surfaces, all of these reflect the underlying geometry of water molecules. The snowflake is like a magnification of the molecular world, enlarged by billions of times, making visible the geometric principles that govern the arrangement of atoms. Water molecules form hexagonal rings when they bond. This is one of the most essential facts about water. When water molecules bond to each other in the frozen state, they naturally form rings that have 6 sides. This is not something that requires effort or outside force. It is the natural, lowest energy configuration for water molecules. 6 molecules form a ring, with each molecule bonded to 2 others in the ring. This hexagonal ring is the fundamental building block of all ice crystals. Hexagonal rings stack in a hexagonal lattice, forming the basic unit of a snowflake. These 6-membered rings don't just exist in isolation. They stack on top of each other, bond to each other, creating a 3-dimensional lattice structure. This lattice has hexagonal symmetry when viewed from above, and it naturally generates 6-fold rotational symmetry in the crystals that form. Every layer of molecules adheres to this hexagonal pattern, creating a structure that is fundamentally 6-sided at every level. Different minerals have different facet structures based on their lattices. Water is not unique in forming crystals. Many minerals form crystals, and each mineral's crystal structure is determined by the arrangement of its atoms or molecules. A diamond has a different facet structure than a ruby, which has a different structure than quartz. Each one reflects the underlying lattice of atoms or molecules that make up that mineral. The snowflake is nature's most delicate example of this principle, but it is a principle that governs all crystalline materials. Snowflakes have 6 side faces called prism facets. If you imagine the basic hexagonal prism shape of a snowflake, the prism facets are the 6 vertical faces that form the sides of the hexagon. These are the prism faces, the faces of the hexagonal prism. They represent the fundamental hexagonal shape of the crystal, extending upward and downward. The top and bottom surfaces are called basal facets. The basal facets are the flat surfaces at the top and bottom of the hexagonal prism. These are different from the prism faces, with a different orientation and often a different growth rate. The distinction between prism facets and basal facets is important in understanding snowflake growth, as the growth rates on these different face types can vary significantly depending on temperature and humidity. The basic shape of small snow crystals is a hexagonal prism. Before a snowflake has grown very large, before it has developed elaborate branches and arms, it exists as a simple hexagonal prism. This is the default form, the most common starting point. The 6 prism faces and the 2 basal faces at top and bottom, these define the basic geometry. Everything that comes later, all the elaborate features and intricate details, develops from this basic hexagonal prism structure. Remnants of this shape are often visible at the center of larger crystals. Even in the most elaborate and ornate snowflakes, if you look carefully at the very center, you may see hints of the original hexagonal prism. The branches and elaborate features grew outward from this central core, but they did not erase it. The original geometry remains at the heart of the crystal, a reminder of how the snowflake began its journey and what path it followed as it grew. The process of faceting is how molecular geometry is transferred to large crystals. This is one of the beautiful aspects of crystal growth. The molecular geometry, which exists at scales invisible to human eyes, is transferred through the crystal growing process to scales where we can see it, touch it, hold it in our hands. The faceting process makes the invisible visible, translating molecular information into macroscopic form. Through faceting, the molecular structure of water becomes visible geometry in the snowflake. Segment 5. Diverse forms and structural complexity. Let us now explore the remarkable diversity of snowflake forms, the many different shapes and structures that emerge from the fundamental hexagonal geometry. While all snowflakes are six-sided, the variations in form are nearly infinite, each reflecting a unique journey through the atmosphere. Columnar crystals may become hollow or grow into thin needles. The columnar form is one of the basic snowflake types, a tall, thin hexagonal prism. But as this form grows, it can evolve in different ways. Sometimes the interior of the column becomes hollow, creating a thin-walled tube rather than a solid block. Other times, the column becomes even more needle-like, stretching upward and downward to create delicate shafts of ice. These variations in how columns develop reflect the specific conditions encountered during growth. Bullet rosettes are clusters of columnar crystals with a tapered look. Imagine several needle-like columns arranged in a cluster, like a bunch of pencils bound together, but with the bundle coming to a point at one end. This creates a rosette pattern, a flower-like arrangement where the columns radiate outward from a central point. The name bullet rosette comes from the resemblance to a cluster of bullets, though the form is far more delicate and beautiful than any weapon. Stellar plates sprout 6 primary branches, forming star-shaped crystals. Stellar snowflakes are among the most iconic and beautiful. Picture a flat hexagonal plate with arms reaching outward from each of the 6 sides of the hexagon. These 6 primary branches create a star-like appearance, hence the name stellar. The branches spread outward, reaching toward the corners that would be natural extensions of the hexagonal geometry. Each primary branch can itself develop secondary branches, creating an intricate pattern that can be breathtakingly beautiful. Fern-like dendritic structures can reach up to 10 millimeters in diameter. Dendrite comes from a word meaning tree-like, and dendritic snowflakes do indeed resemble delicate trees or ferns. The structure develops with a main stem and many branches coming off at angles, creating a fractal-like appearance where patterns repeat at different scales. These fern-like snowflakes are among the largest forms, and their delicate structure makes them fascinating to observe. Side branches are always separated by multiples of 60 degrees. This is an essential fact that flows from the hexagonal geometry. The angles in a hexagon are all 120 degrees, and the arms of a snowflake are separated by 60-degree intervals. When side branches form on the primary arms, they too follow this 60-degree rule. The geometry is consistent throughout the crystal, from the largest branches down to the smallest details. There is an orderliness to the branching pattern, a mathematical regularity that underlies the apparent freedom of growth. Capped columns are rare and exotic, with 2 plates on the ends of a column. These remarkable crystals represent a specific kind of growth history. The snowflake began as a column, growing in a columnar regime, but then encountered conditions that favored plate-like growth. When it did, flat hexagonal plates formed on the top and bottom of the column, like caps. The result is a form that combines both columnar and plate-like features, creating a structure that is rare and visually striking. Perfect symmetry is more the exception than the rule in snowflakes. This might seem surprising given how much we have discussed the mathematical symmetry inherent in snowflakes. Yet in reality, perfect six-fold symmetry is actually uncommon. Most snowflakes show some asymmetry, with the six arms being not quite identical to each other. This asymmetry emerges from the tiny variations in the microenvironment around different arms as the snowflake grows. Even though the conditions are similar on all sides, they are not perfectly identical, and this creates subtle differences in how the arms develop. Elaborate structures develop as crystals grow larger. There is a relationship between size and complexity. A small snowflake, having only fallen a short distance through the atmosphere, will have relatively simple structure. A larger snowflake, having fallen further and encountered more varied conditions, will have had more time to develop elaborate features. The journey through the atmosphere is a journey toward complexity, from simple prism to increasingly intricate form. The stunning variety of shapes is a result of changing conditions. When we marvel at the diversity of snowflake forms, we are really marveling at the diversity of atmospheric conditions. Each snowflake is unique because its path through the atmosphere was unique. The temperature changes it encountered were unique, the humidity levels it passed through were unique, the duration of its journey was unique. The snowflake is a mirror of the atmosphere, reflecting back to us the atmospheric journey it has taken. Snowflakes exemplify fractals, with patterns repeating at different scales. A fractal is a geometric form where patterns repeat at different levels of magnification. Snowflakes are prime examples of fractals. Look at a branch of a snowflake, and you see a pattern. Look at the secondary branches on that primary branch, and you see a similar pattern at a smaller scale. This self-similar repetition of patterns at different scales is characteristic of fractals, and it reflects the way snowflakes grow, with branching processes that repeat across different size scales. As we contemplate this diversity of forms, we begin to appreciate that the snowflake is not a single thing, but rather a family of things. All snowflakes share the same fundamental six-fold geometry, yet each member of this family has a unique form. This combination of unity and diversity, of fundamental order combined with infinite variation, is one of the most beautiful aspects of snowflakes. Segment sacks, temperature regimes, and growth patterns. Let us now turn our attention to how temperature specifically affects snowflake formation. Temperature is one of the two primary variables that determine snowflake form, and the relationship between temperature and snowflake morphology is one of the most consistent patterns in crystal formation. The stunning six-limb star-like crystals form in temperatures above -15 degrees Celsius. Actually, we need to be more precise. Above -15 degrees Celsius or thereabouts, stellar and dendritic crystals form, creating those beautiful star-like structures with extending arms and intricate branches. These are the snowflakes that most people imagine when they think of snowflakes, the classic six-pointed stars. They form in the relatively warm upper atmosphere, where temperatures are cold enough for ice to form, but not so cold as to suppress branching. Between -15 degrees Celsius and -24 degrees Celsius, snow falls as small prisms and simple plates. This temperature range creates conditions for different growth patterns than we saw in warmer regions. Instead of elaborate stellar crystals with extending arms, the crystals in this range tend to form simple columnar prisms or flat hexagonal plates. These are less elaborate in their decoration, but still beautiful in their geometric simplicity. Between -24 degrees Celsius and -8 degrees Celsius, small stars form again. We return to stellar forms, though these are often simpler than the stars that form at warmer temperatures. This temperature regime brings back the conditions that favor branching, though perhaps not to the same degree as in the warmer regions. The stars that form here are often smaller and less elaborate, but they still maintain that characteristic star-like six-pointed appearance. Below -8 degrees Celsius, the prism shape returns. At the coldest temperatures, we see a return to simple columnar forms, columnar prisms that are relatively unadorned. At these extreme cold temperatures, the growth conditions favor the formation of simple shapes. The branching processes that create elaborate features are suppressed, and the crystal grows into relatively straightforward geometric forms. These simple prisms have their own beauty, the beauty of pure geometry and elegant simplicity. The growth rate of different facets determines the final shape. We have mentioned this before, but it is worth returning to as it is so fundamental. The rate at which different faces of the crystal grow is the key variable. If the basal faces grow much faster than the prism faces, the crystal will tend to form a thin, flat plate. If the prism faces grow faster, the crystal will form a tall column. The relative growth rates of different crystal faces are determined primarily by temperature and humidity, with temperature being one of the primary factors. The shape of snowflakes is determined by the properties of water molecules. This is the deepest truth underlying all snowflake formation. The shapes we observe, the patterns we marvel at, the diversity of forms, all of this emerges from the properties of water molecules. The hexagonal geometry, the preference for certain growth directions, the branching patterns, the response to temperature and humidity. All of these properties are built into the water molecule itself. The snowflake is simply expressing what is inherent in its chemical nature. The lowest energy structure for water molecules is a crystal with six-fold symmetry. When water freezes, it naturally tends toward the structure that requires the least energy to maintain. That structure is one with six-fold symmetry. This is not a law imposed from outside, but rather a natural tendency of the system. Just as a rolling ball tends to settle in the lowest point in the landscape, water molecules tend to arrange themselves in the configuration that is lowest in energy. That configuration is hexagonal, six-fold symmetric, and it is the foundation of all snowflake structure. The formation and shape of snowflakes are influenced by temperature and humidity. These are the two master variables. We have discussed them separately, but they work together. The combination of temperature and humidity determines the growth rates on different faces of the crystal, determines whether faceting or branching dominates, determines the size and complexity of the snowflake. A particular temperature and humidity combination creates particular growth conditions, and these conditions produce particular snowflake morphologies. Snow crystals can grow into a variety of forms depending on facet growth. The diversity of forms we observe is a direct result of the fact that different faces of the crystal grow at different rates. If all faces grew at the same rate, all snowflakes would have the same form. The variation in growth rates among different crystal faces is the source of the extraordinary variety of snowflake structures. This variation itself is determined by temperature and humidity, which affect growth rates differently on different crystal faces. At temperatures around -22 degrees Celsius, snowflakes often form plate-like or columnar shapes. This specific temperature range is particularly interesting because it is a transition point. Right around this temperature, the growth rates on different faces change in ways that produce the plate and columnar forms. This temperature is like a boundary between regimes, where the crystal geometry shifts from one type to another. As we understand how temperature controls snowflake form, we gain insight into the atmosphere itself. By examining snowflakes, scientists can infer the temperature profile through which each crystal fell. The snowflake becomes a thermometer, a record of temperatures at different altitudes. In this way, the snowflake tells us about the atmosphere's temperature structure, revealing the hidden layers and temperature variations that the crystal encountered during its descent. Segment 7. The Cosmic Dance of Growth and Descent. Let us now expand our view, pulling back to see the snowflake not as a static object, but as a dynamic entity engaged in an ongoing dance with the atmosphere as it falls from the clouds toward the Earth. As snowflakes fall, they collect more water molecules and form branches. This image captures something essential about snowflake growth. The crystal does not simply start fully formed in the cloud. Rather, it begins as a tiny seed and grows as it falls. With each moment of the descent, with each layer of atmosphere the crystal passes through, it collects more water molecules. These accumulate on the crystal's surface, adding to its structure, extending its geometry. The branching that creates elaborate features happens during this descent, not before it. The patterns depend on temperature and humidity. We have mentioned this before, but here we focus on it in the context of the entire descent journey. As the snowflake falls, it experiences a series of temperature and humidity conditions. Each of these conditions shapes the growth of the crystal. A layer of high humidity causes rapid branching. A layer of lower temperature causes a shift to different growth patterns. The descent is a journey through a series of conditions, each one leaving its mark on the developing crystal. Snowflakes are beautiful and complex structures formed by freezing water vapor. Let us appreciate this simple statement. Water vapor, which is invisible, which has no structure of its own, freezes into a crystal with sixfold symmetry. This transformation from invisible gas to visible, structured crystal is one of nature's most remarkable processes. The invisible becomes visible, the formless becomes geometric, the plane becomes beautiful. This is the essence of snowflake formation, the transformation of water vapor into crystalline beauty. The variety of snowflake shapes is a result of changing conditions. Each time we see a snowflake with a different form, we are seeing a direct result of the conditions it experienced during growth. A snowflake with elaborate stellar branches experienced conditions that favored branching. A simple plate experienced conditions that suppressed branching. A capped column experienced a transition between columnar and plate-like conditions. The form of the snowflake is a story, and the chapters of that story are written by the conditions the crystal experiences. The intricate patterns are a result of the water molecule's structure. When we admire the intricate patterns and details of a snowflake, we are admiring the direct result of water's molecular structure. The patterns are not random, not arbitrary. They emerge necessarily from the way water molecules bond to each other. The molecular geometry determines what patterns are possible, and then the specific growth conditions determine which patterns actually emerge. The snowflake is a manifestation of chemistry made visible. Each snowflake's arms grow independently from the corners of the hexagon. Although this may seem to suggest randomness, it is actually a crucial fact about snowflake growth. Each arm grows independently in response to the local conditions around that arm. This independence is why snowflakes are not perfectly symmetric. If all arms had identical conditions around them at all times, they would grow identically. But the conditions are never perfectly identical around all 6 arms. This leads to the subtle asymmetries that make each snowflake unique, even as all snowflakes are bound by the same fundamental geometry. The unique conditions for each snowflake ensure no two are alike. This famous fact about snowflakes is now comprehensible to us. Given everything we have learned about the many variables that affect snowflake growth, given the sensitivity of crystal formation to small changes in temperature and humidity, given the complexity of the descent through the atmosphere, it becomes clear why 2 snowflakes would never have identical growth histories. The probability that 2 snowflakes would encounter the exact same temperature and humidity profile during their descent is virtually 0. Therefore, no 2 snowflakes are exactly alike. No 2 snowflakes are exactly alike due to unique atmospheric conditions. This statement is the culmination of everything we have discussed. The uniqueness of snowflakes is not mysterious or miraculous. It is a direct consequence of the physics of crystal growth in a complex, variable atmosphere. Every snowflake is unique because the atmosphere is not uniform. Every snowflake's form is determined by the conditions it experiences. And because each snowflake experiences slightly different conditions during its descent, each emerges with a unique form. Snowflakes experience changing temperatures and humidity as they fall through the atmosphere. The journey downward is never a journey through uniform conditions. The atmosphere is layered, stratified, with different temperatures at different altitudes, with different humidity levels at different locations and times. As the snowflake falls, it passes through all of these variations, experiencing a constantly changing environment. The snowflake's growth is responsive to this changing environment, adjusting its growth patterns in response to the changing conditions. Each change in environment alters the crystal's growth pattern. When the snowflake passes from a region of high humidity to a region of lower humidity, its growth mode changes. When it passes from a warmer layer to a colder layer, the growth patterns shift. These changes are not discrete, not abrupt, but gradual. The crystal's growth continuously responds to the changing conditions around it. In this way, The snowflake becomes a living document of the atmosphere's structure, a record written in ice of the conditions that created it. Segment 8: Mathematical Models and Fractal Structures. Now let us explore the mathematical dimensions of snowflake formation, the way that geometry, symmetry, and the mathematics of fractals help us understand and describe these remarkable crystals. The mathematics of snowflakes involves geometry, symmetry, and group theory. These are the mathematical tools that scientists use to describe and understand snowflakes. Geometry describes the shapes and spatial relationships. Symmetry helps us understand the invariances and regularities. Group theory is the mathematical language of symmetry, providing formal tools for describing how symmetries operate and interact. Together, these mathematical frameworks provide a complete description of snowflake structure. Geometry describes the shapes and arrangements of water molecules. When water molecules arrange themselves in a crystal, they form a geometric structure. This structure can be described using geometric language, the language of angles, distances, surfaces, and three-dimensional forms. Geometry allows us to translate the microscopic arrangement of molecules into descriptions of the macroscopic snowflake form. It provides the language for describing exactly how the atoms are arranged. The geometry of snowflakes is a result of the molecular structure of water. This is the link between the microscopic and macroscopic worlds. The geometry we observe in large snowflakes emerges necessarily from the geometry of water molecules. The hexagonal shape emerges from the way water molecules bond. The six-fold symmetry emerges from the six-fold symmetry inherent in the water molecules' bonds. The macroscopic geometry is literally an enlargement of the microscopic geometry. The six-fold symmetry is a direct result of the hexagonal lattice. We have discussed hexagonal lattices before, but here we emphasize that the six-fold symmetry we observe in snowflakes is not something added to the lattice from outside. It is an inherent property of the hexagonal lattice itself. A hexagonal lattice has six-fold rotational symmetry by definition. Place that symmetry on the microscopic scale, magnify it through the crystal growth process, and it emerges at the macroscopic scale as the six-fold symmetry of snowflakes. Snowflakes can also display 12-fold symmetry, a multiple of 6. Some rare snowflakes show 12-fold symmetry instead of 6-fold symmetry. This happens when the snowflake grows in a way that brings two layer structures together. The resulting structure has 12-fold symmetry, which is 2 times 6-fold, mathematically harmonious, and perfectly consistent with the rules of crystal geometry. These snowflakes are unusual, but they demonstrate how the fundamental 6-fold symmetry can combine to create even larger symmetries. 8-sided snowflakes are not possible due to water's molecular structure. Water molecules cannot arrange themselves in a way that produces 8-fold symmetry. The bonding angles in water molecules, the fundamental geometry of water's chemical structure, makes 8-fold symmetry impossible. You will never find a snowflake with 8 sides, or 4 sides, or 5 sides. The molecular structure is strict in enforcing 6-fold or multiples of 6-fold geometry. This is a fundamental constraint built into the nature of water. Fractals are pervasive in nature, and snowflakes are a prime example. A fractal is a geometric form that exhibits self-similarity across scales. Snowflakes exemplify fractals with branching patterns that repeat at different scales. Look at a snowflake at 1 magnification and you see branches. Look at these branches more closely and you see smaller branches with similar shapes. This self-similarity across scales is the hallmark of fractals, and snowflakes are among nature's most beautiful examples. Snowflakes exemplify fractals, with patterns repeating at different scales. This means that the overall branching pattern of the snowflake resembles the pattern of individual branches. A branch of a snowflake looks like a smaller version of the whole snowflake. The secondary branches on a primary branch look like smaller versions of primary branches. This self-similar repetition at different scales is what makes snowflakes fractals. It also explains some of the diversity of snowflake forms. Because of this self-similar structure, snowflakes can develop extraordinarily elaborate forms while still remaining bound by simple rules. The Koch snowflake curve is a mathematical model inspired by snowflake patterns. The Koch snowflake is a famous mathematical object created by mathematician Helge von Koch. It is constructed by taking a triangle and replacing each side with a bump, creating a more complex shape. This process is repeated infinitely, creating a shape that has infinite complexity. Though this mathematical construction is different from actual snowflakes, it shares essential properties with them. It is fractal, self-similar, and infinitely complex, despite being constructed from simple rules. Snowflakes can be modeled using mathematical equations. Scientists have developed mathematical models that can simulate snowflake growth. These models incorporate the rules of crystal growth, the effects of temperature and humidity, the dynamics of water molecule attachment. By running these models, researchers can generate simulated snowflakes that closely resemble real snowflakes. These models reveal that the complexity of snowflake forms emerges from relatively simple underlying rules and processes. This is the essence of complexity, the way that complex, beautiful structures emerge from simple laws. The beauty of snowflakes is a result of their intricate geometry. When we admire a snowflake, we are admiring geometry. We are admiring the expression of mathematical principles in physical form. The branching patterns follow geometric principles. The symmetries follow group theory. The self-similarity follows fractal geometry. The beauty that we perceive is the beauty of mathematics made visible. In this sense, every snowflake is a work of mathematical art, an expression of abstract principles in concrete form. Segment 9. The formation process and crystal nucleation. Let us now journey into the earliest moments of snowflake formation, the moment when a snowflake is born from water vapor in the cold clouds. Snow crystals start as small, faceted prisms about the size of a period on a page. This is how every snowflake begins. In the clouds, where temperatures are below freezing, water vapor condenses onto tiny particles of dust, salt, or other nucleating particles. On these microscopic nuclei, water molecules begin to accumulate, freezing as they do so. The first structure to form is a hexagonal prism, usually very small, often just a few micrometers across. This tiny crystal is the seed from which the entire snowflake will grow. Depending on how the conditions evolve around them, these minuscule prisms can grow into very different forms. This is the crucial point where the crystal's future direction is determined. The temperature and humidity around the tiny prism will govern how it grows. If the conditions favor columnar growth, the prism will extend upward and downward, becoming a thin needle. If the conditions favor plate-like growth, the prism will flatten and spread, becoming a thin disk. The earliest moments of the crystal's existence set it on a path that will govern its entire future development. Some become slender columns, reaching and extending upward and downward. A columnar snowflake grows primarily in the vertical direction, along the axis of the prism. The basal faces, the top and bottom, grow very slowly, while the prism faces on the sides grow more rapidly vertically. The result is a thin, needle-like structure. These columns can become very elongated, sometimes growing to be a millimeter or more in length, yet remaining very narrow. Others flatten into thin plates, spreading their geometry across the sky. A plate-like snowflake grows rapidly on the basal faces, the top and bottom, while the prism faces grow much more slowly. The result is a thin, flat disk, a hexagonal plate. These plates can grow to be quite large in their horizontal extent while remaining very thin. The plate structure creates different growth conditions for the side faces, sometimes leading to the development of elaborate arms and branches. The basic geometry is a hexagonal prism, but variations abound. This statement captures the essential principle of snowflake diversity. All snowflakes begin as hexagonal prisms, but from there the variations are numerous. The columnar versus plate-like distinction is just one way to divide them. Within each of these categories, there are further variations. The fundamental hexagonal prism shape is the foundation upon which all of these variations build. The variety of snowflake shapes is a result of environmental factors. We have said this many times, but here we emphasize it in the context of the formation process. The shape that emerges is determined by the environment. Change the environment and you change the shape. This is why snowflakes from different parts of the cloud will have different forms. Different altitudes in the cloud have different temperatures and humidities. Snowflakes that fall through different parts of the cloud encounter different conditions and grow into different forms. Elaborate structures develop as crystals grow larger. As the crystal descends through the cloud and the atmosphere below, it has time to grow. The longer the descent, the larger the crystal becomes. And as it grows larger, the growth conditions can create increasingly elaborate structures. A crystal that has traveled a long distance has had a long time to grow and has encountered many different growth regimes. This long journey allows time for the development of elaborate features, for the growth of branches and sidearms and delicate details. The molecular structure of water ensures that all snowflakes have 6 sides. At the moment of nucleation, when the first water molecules accumulate on a dust particle, the molecular structure of water begins to govern the crystal's form. The angles between bonds in water molecules ensure that the resulting crystal will have 6 sides. This is determined from the very first moment, from the instant that the first water molecules freeze onto the nucleus. The 6-fold geometry is not added later. It is present from the beginning, governing every step of the crystal's development. Faceting and branching compete to shape snowflake patterns. From the moment the crystal forms, these two forces are in play. Initially, faceting dominates in the small crystal, creating smooth, regular faces. But as the crystal grows and the conditions change, branching may take over, creating arms and features. Throughout the crystal's life, as it falls through varying atmospheric conditions, these two forces compete, creating the final form of the snowflake. The balance of these forces creates the beauty of snowflakes. The final form of the snowflake is the result of the balance between faceting and branching, between the forces that create simple, regular geometry and the forces that create complex, elaborate features. When one force dominates, the snowflake is either very simple or very elaborate. When the forces are balanced, the snowflake achieves a kind of perfect harmony, neither too simple nor too complex. This harmony is one of the things that makes snowflakes beautiful. Segment 10. Symmetry, asymmetry, and the near-perfect crystal. Let us now explore one of the most subtle and fascinating aspects of snowflakes, the interplay between the near-perfect symmetry we expect and the actual asymmetries that often emerge. Reflection symmetry allows a snowflake to look the same when flipped over 3 different axes. We have discussed this before, but now let us contemplate what it means. If you take a snowflake and hold it before a mirror, the reflected image should look identical to the original. And this works not just for one direction of reflection, but for 3 different mirror planes. This 3-fold reflection symmetry, combined with 6-fold rotational symmetry, creates a structure that is mathematically complete and perfectly balanced. Perfect symmetry is more the exception than the rule in snowflakes. Yet here we encounter something surprising. Given how much we have emphasized the symmetry of snowflakes, we might expect perfect symmetry to be common. In fact, it is rare. Most snowflakes show some degree of asymmetry, with the 6 arms being slightly different from each other. This asymmetry is not a flaw or a failure. It is natural and expected, the result of the fact that no 2 arms of a snowflake experience absolutely identical conditions as they grow. The arms of a snowflake are always separated by 60 degrees. Even when the arms are not perfectly identical in form, they are always separated by the same angular distance. This angular regularity persists even when the shapes are not perfectly symmetric. This tells us that the hexagonal geometry is fundamental and inviolable, while the details of how that geometry is elaborated can vary. The 6-fold structure is preserved even as the perfect symmetry is broken. The patterns on a snowflake are a result of its growth history. Here we return to an idea that we have touched on many times. The snowflake is a record of its growth history. If you could read a snowflake like a book, you would be reading the story of the atmospheric conditions it encountered during its descent. A thickening of certain arms tells you that there was a period when those arms encountered better growth conditions. A sudden shift in the branching pattern tells you that the temperature or humidity changed. The asymmetry of the snowflake reflects the asymmetry of conditions it experienced. The unique conditions for each snowflake ensure no 2 are alike. Let us now think about what this means more deeply. The atmosphere is a chaotic system. Small differences in position or timing can lead to large differences in conditions. A snowflake that forms 1 second later or 1 meter over experiences different conditions. These different conditions lead to different growth patterns. And because the number of snowflakes is so large, and the number of possible paths through the atmosphere is so large, the probability that 2 snowflakes would follow identical paths and experience identical conditions is essentially 0. The molecular structure of water is the foundation of snowflake geometry. This is the deepest truth. Every aspect of snowflake structure, from the most obvious symmetry to the subtlest asymmetry, emerges from the way water molecules bond to each other. There is no separate set of rules imposed from outside. The rules are intrinsic to water. Water, in its frozen state, naturally tends toward these hexagonal structures and sixfold symmetries. The snowflake is simply water being itself, expressing its intrinsic properties. The hexagonal lattice is the key to snowflake symmetry. The lattice is the scaffolding upon which snowflake growth builds. As water molecules freeze, they arrange themselves in a hexagonal lattice. This lattice has built-in sixfold symmetry. The snowflake that grows from this lattice naturally expresses this symmetry in its large-scale form. The lattice structure is both the cause and the foundation of snowflake symmetry. The geometry of snowflakes is a beautiful example of nature's symmetry. When we say that snowflakes are beautiful, we are saying that their geometry is beautiful, that symmetry is beautiful. Mathematical symmetry, when expressed in physical form, is aesthetically pleasing. This is not accidental. The human eye and brain have evolved to find symmetry beautiful. And snowflakes, being expressions of mathematical symmetry, naturally appeal to our sense of beauty. The arms of a snowflake grow independently from the corners of the hexagon. Although the arms are separated by 60 degrees, the growth of each arm is not rigidly controlled by some central authority. Rather, each arm responds independently to the local conditions around it. This independence creates the potential for asymmetry while maintaining the overall hexagonal structure. The snowflake is simultaneously a perfectly organized structure in its large-scale geometry and a record of local, independent processes in the details of how each arm developed. The interplay of faceting and branching creates the beauty of snowflakes. We have seen how faceting and branching are competing forces. Faceting creates simple, regular geometry. Branching creates complex, elaborate structures. The beauty of snowflakes emerges from the balance and interplay of these forces. A snowflake where one force dominates completely would be either too simple or too chaotic. The snowflakes we find most beautiful are often those where the forces are balanced, creating a harmony of simplicity and complexity. Segment 11. The diversity of crystal types and formations. Let us now deepen our understanding of the various crystal types and formations, exploring the full range of snowflake morphologies and how each type emerges under specific conditions. Columnar crystals may become hollow or grow into thin needles. We have mentioned columns before, but now let us explore the range of columnar forms. A simple columnar crystal is a solid hexagonal prism extended in the vertical direction. But as it grows, the interior may hollow out, creating a thin-walled tube rather than a solid form. This hollow core can develop into regular patterns, with the walls becoming very delicate and thin. Alternatively, the column may extend into a thin needle, becoming so narrow and pointed that it resembles nothing so much as a natural needle of ice. Bullet rosettes are clusters of columnar crystals with a tapered look. These are among the most unusual and striking snowflake forms. Instead of a single crystal, a bullet rosette consists of multiple columnar crystals clustered together. The individual crystals are arranged in a way that creates an overall tapered, pointed appearance, like a cluster of bullets. These clusters form when multiple nucleation sites are present, and they grow together into a unified structure. They are relatively rare but visually distinctive. Stellar plates sprout 6 primary branches, forming star-shaped crystals. The stellar snowflake is perhaps the most iconic snowflake form. Picture a flat hexagonal plate with 6 arms extending outward from the corners of the hexagon. These arms, called primary branches, extend in the directions that naturally follow from the hexagonal geometry. Each primary branch points toward a corner of the hexagon that would exist if you extended the hexagonal pattern outward. These stellar crystals can be remarkably beautiful, with each arm elaborately decorated with smaller branches and features. Fern-like dendritic structures can reach up to 10 millimeters in diameter. Dendrite means tree-like, and dendritic snowflakes do resemble trees or ferns. The dendritic form develops when there is rapid growth, often in conditions of high humidity and favorable temperatures. The primary structure is a main axis with many branches coming off at regular angles, creating a fractal-like appearance where the pattern repeats at smaller scales. These snowflakes can grow quite large, and their intricate branching patterns can be breathtakingly complex. Side branches are always separated by multiples of 60 degrees. This is a beautiful example of how the hexagonal geometry constrains all aspects of snowflake structure. Not just the primary arms, but even the smallest side branches follow this rule. The branching angles are always multiples of 60 degrees. This is not something the snowflake chooses. It is built into the geometry of the hexagonal lattice. Every angle in the structure reflects the underlying 6-fold symmetry. Capped columns are rare and exotic, with 2 plates on the ends of a column. These remarkable forms represent a specific kind of temperature history. The snowflake begins growing as a column, with growth favored along the vertical axis. But then the environmental conditions change. The temperature or humidity shifts in such a way that plate-like growth becomes favored. When this happens, the top and bottom of the columnar crystal begin to expand outward, creating flat plates. The result is a structure that combines columnar and plate-like features, with a tall, thin central column capped by flat hexagonal plates on top and bottom. Plates can be simple hexagons, stellar in appearance with extended branches, or sectored with prominent ridges. The plate is another fundamental snowflake form, a flat hexagonal disc. In its simplest form, it is just a hexagon, but as it grows, it can develop stellar branches, with arms extending outward from the sides of the hexagon, or it can develop sectoring, with the plate divided into distinct sectors separated by ridges or lines. Each of these variations represents a different growth history, a different combination of temperature and humidity conditions. Occasionally, snowflakes form rare triangular crystals with only 3 sides. This is one of the most surprising facts about snowflakes. Given how fundamental 6-fold symmetry is to snowflake formation, one might think that triangular crystals would be impossible. Yet they do form, though rarely. These triangles are actually related to the hexagon, emerging when growth conditions somehow favor 3-fold symmetry instead of 6-fold. They are anomalies that remind us that nature sometimes deviates from the norm in unexpected ways. Depending on growth, these prisms can become slender columns or thin plates. This captures the essential branching point in snowflake development. The tiny hexagonal prism that forms initially can develop in very different directions depending on the growth conditions it encounters. The balance between basal growth and prism face growth determines whether it becomes columnar or plate-like. This is the first major decision point in the snowflake's development, and it sets the course for all that follows. The growth rate of different facets determines the final shape. The growth rate is the key variable. Different faces of the crystal grow at different rates, and these rates are determined by temperature and humidity. A high growth rate on the basal faces combined with low growth rate on the prism faces creates plates. The opposite creates columns. By understanding which faces are growing fast and which are growing slow, we can predict which forms will develop. Snow crystals can grow into a variety of forms depending on facet growth. This statement summarizes the relationship between growth rates and final form. The tremendous diversity of snowflake types is not due to randomness or arbitrary variation. It is due to the systematic differences in growth rates on different crystal faces under different environmental conditions. Understanding growth rates is understanding snowflakes. The two are inseparable. Segment 12. The nature of water and the foundations of structure. Let us now venture into the deepest foundations of snowflake formation, exploring the essential properties of water that make snowflakes possible. Water molecules form hexagonal rings when they bond. This is one of the most fundamental facts about water in its solid state. When water molecules freeze, they bond to each other in a very specific way. 6 water molecules can form a ring, with each water molecule bonded to exactly 2 others in the ring. This hexagonal ring is the smallest possible unit that exhibits the hexagonal geometry that characterizes ice. From this small ring, all larger structures build upward. Hexagonal rings stack in a hexagonal lattice, forming the basic unit of a snowflake. The rings do not remain isolated. They bond to other rings, creating layers. These layers stack on top of each other, bonding vertically as well as horizontally. The result is a 3-dimensional lattice structure with hexagonal symmetry when viewed from above. This lattice is the scaffold upon which snowflake crystals grow. Every snowflake, no matter how elaborate or complex, is fundamentally an extension of this hexagonal lattice. Different minerals have different facet structures based on their lattices. Water is not unique in forming crystals. Many mineral compounds form crystals, each with its own characteristic structure based on its molecular arrangement. Quartz crystals form 6-sided crystals, but with different proportions than ice. Diamond forms cubic crystals. Mica forms layered crystals. Each mineral's characteristic crystal form flows from the arrangement of its atoms or molecules. The snowflake is simply water expressing its particular crystalline nature. The angle between water molecules mandates the hexagonal ice lattice. The key to understanding why water forms hexagonal ice is to understand the angle at which water molecules bond. The water molecule has a bent shape, with oxygen in the center and two hydrogen atoms at an angle. When water molecules bond to each other, they do so at an angle that naturally leads to the formation of hexagonal rings and hexagonal lattices. The angle is not something that was chosen or imposed from outside. It is an intrinsic property of the water molecule. The molecular lattice determines which surfaces grow slowly and which grow rapidly. Not all surfaces of a crystal are equivalent. The hexagonal lattice has surfaces with different orientations, and these surfaces have different arrangements of atoms on them. Some surfaces have atoms arranged in a way that makes it easy for new molecules to attach. Other surfaces are more resistant. These differences in growth rate are fundamental to understanding how crystal shapes develop. The relative growth rates on different surfaces are one of the primary determinants of final crystal form. Facetting reveals the geometry of the water molecule in large crystals. This is a beautiful consequence of how crystals grow. The molecular geometry that exists at submicroscopic scales, invisible to the human eye, is revealed and magnified in large crystals through the process of faceting. A flat face on a crystal corresponds to a particular orientation of the molecular lattice, an orientation that grows slowly and thus shows up as a visible surface. The large-scale geometry of the snowflake is literally a magnified version of the molecular geometry. The basic shape of small snow crystals is a hexagonal prism. This is the default form, the shape that emerges when a water crystal is allowed to grow under simple conditions. The hexagonal prism has 6 prism faces on the sides and 2 basal faces on the top and bottom. This is the simplest crystal form that expresses the hexagonal lattice structure of ice. More complex forms develop only when growth conditions vary, creating instability or favoring specific directions of growth. Remnants of this shape are often visible at the center of larger crystals. No matter how elaborate a snowflake becomes, if you look at its center, you will often see hints of the original hexagonal prism. The branches and arms grew outward from this central structure, but they did not erase it. The original form remains at the heart of the crystal, like the core of a tree, recording the earliest stage of the snowflake's development. This is a visible reminder that all snowflakes, no matter how diverse, share a common origin in the simple hexagonal prism. The process of faceting is how molecular geometry is transferred to large crystals. This is the mechanism by which invisible atomic scale information becomes visible crystalline structure. As the crystal grows, the faceting process continuously transfers molecular level information to the macroscopic scale. The result is that the large crystal carries information about molecular geometry in its form. This transfer of information from small scales to large scales is one of the most elegant aspects of crystal formation. Faceting and branching compete to shape snowflake patterns. These two opposing forces create a dynamic tension that shapes the snowflake. When faceting dominates, the crystal grows into simple, regular forms. When branching dominates, complex structures emerge. The competition between these forces creates the diversity of snowflake forms. Different temperatures and humidity levels tip the balance between these forces, creating different snowflake forms. The balance of faceting and branching creates the intricate patterns. The final form of the snowflake is the result of the balance and interplay of these competing forces. When faceting and branching are balanced, the result is a snowflake that combines simple, regular geometry with intricate, elaborate detail. This balance is what creates many of the most beautiful snowflakes. Those that are neither too simple nor too chaotic, but instead achieve a kind of perfect harmony. Segment 13. Thermodynamics, energy, and crystal preference. Let us now explore the thermodynamic principles that govern snowflake formation, understanding why certain forms emerge as nature's preferred structures. The lowest energy structure for water molecules is a crystal with six-fold symmetry. This is a statement rooted in thermodynamics, the branch of physics that deals with energy and the tendency of systems to move toward lower energy states. When water freezes, the water molecules arrange themselves in the configuration that minimizes energy. That configuration is a hexagonal lattice with six-fold symmetry. This is not something that requires external force or engineering. It is the natural tendency of water, the path that the system naturally follows. The molecular structure of water is the foundation of snowflake geometry. Because the lowest energy configuration is hexagonal, all snowflakes are hexagonal. The six-fold symmetry is not decoration or ornamentation. It is the foundation, the fundamental principle upon which all snowflake structure rests. Change the molecular structure of water, and you would change snowflakes. But water is water. Its molecular structure is fixed, and therefore snowflake geometry is fixed. The formation and shape of snowflakes are influenced by temperature and humidity. While the hexagonal geometry is fixed by water's molecular structure, the specific form that the hexagon takes is determined by temperature and humidity. These variables affect the growth rates on different crystal faces, causing the crystal to develop in particular directions. In this way, temperature and humidity shape the surface features, while the underlying hexagonal geometry is preserved. The hexagonal lattice is the key to snowflake symmetry. The lattice provides the foundation for all symmetry. The six-fold rotational symmetry of snowflakes is built into the hexagonal lattice. The reflection symmetries are built into the lattice. The regularity and mathematical precision of snowflake geometry all flow from the lattice structure. The lattice is the source, and everything else is elaboration of that basic structure. The geometry of snowflakes is a result of the molecular structure of water. We keep returning to this idea because it is so fundamental. Every aspect of snowflake geometry, from the largest scale symmetries down to the smallest scale details, is ultimately a consequence of the way water molecules are structured and bond to each other. There is no external designer, no set of arbitrary rules. There is only water being itself, expressing what is built into its chemical nature. The six-fold symmetry is a direct result of the hexagonal lattice. The lattice has six-fold symmetry, and the snowflake that grows from the lattice inherits this symmetry. This is not a coincidence. It is a necessary consequence of the lattice structure. Change the lattice to something else, and the symmetry changes. But as long as the lattice is hexagonal, six-fold symmetry is inevitable. The arms of a snowflake grow independently from the corners of the hexagon. Independence at the local level creates the possibility for diversity while maintaining order at the global level. Each arm grows in response to the local conditions around it, but all arms are constrained to grow from the corners of the hexagonal structure. This constraint guarantees the overall symmetry, while the independence of each arm creates the possibility for asymmetry and variation. The unique conditions for each snowflake ensure no two are alike. The uniqueness of snowflakes is not a mystery once we understand how sensitive crystal growth is to atmospheric conditions. Given the complexity of the atmosphere and the vast number of possible paths a snowflake might take through it, uniqueness is not just possible, it is inevitable. Every snowflake is unique because the conditions it experiences are unique. The molecular structure of water ensures that all snowflakes have six sides. The molecular bonds in water create angles that are incompatible with any crystal system other than hexagonal. A snowflake cannot be square or triangular or five-sided, not because someone decreed it so, but because water molecules do not bond in ways that would create those forms. The six-sided form is not optional. It is mandatory, flowing from the very nature of water. Snowflakes are nature's exquisite mathematical masterpieces. With all that we have learned about the mathematical precision and geometric elegance of snowflakes, we can understand why they deserve this designation. Snowflakes are not random or arbitrary. They are expressions of mathematical principles made visible and tangible. In a snowflake, we see mathematics living in nature, abstract principles manifested in ice and water. Segment 14. Contemplating the cosmic significance of snowflakes. As we approach the conclusion of our journey into snowflakes, let us take a step back and contemplate the larger significance of these remarkable crystals and what they teach us about nature and ourselves. Snowflakes are beautiful and complex structures formed by freezing water vapor. This simple description contains profound truth. From something invisible and formless, something as ethereal as water vapor, emerges something visible and structured, something as concrete and tangible as a snowflake. This transformation is a microcosm of how nature works, how simple elements combine to create complexity, how order emerges from what appears formless. The stunning six-limb star-like crystals form in temperatures above -15 degrees Celsius. These are the snowflakes that capture our imagination, that we think of when we think of snowflakes. They are beautiful because their size and complexity make their geometric perfection visible to the human eye. We can hold them in our hands or catch them on our sleeves and actually see the mathematical precision that governs their form. The intricate patterns are a result of the water molecule's structure. Every time we admire a snowflake, we are admiring water. We are admiring the direct expression of how water molecules bond, how they prefer to arrange themselves, what forms they naturally assume when frozen. In a sense, every snowflake is a portrait of the water molecule, a magnified image showing what the water molecule's structure looks like when enlarged billions of times. The formation of snowflakes is a complex process influenced by many factors. Yet underlying this complexity are simple principles. Water molecules bond in hexagonal rings. These rings stack into hexagonal lattices. Temperature and humidity affect growth rates. Branching and faceting compete. From these simple elements, the extraordinary diversity of snowflakes emerges. This is the essence of nature's creativity, the way that complexity emerges from simple rules and principles. The beauty of snowflakes is a result of their symmetry and geometry. We respond aesthetically to symmetry. Mathematical precision has an inherent beauty. Snowflakes combine both in crystalline form. The beauty we perceive is not arbitrary or subjective. It reflects objective geometric properties, mathematical symmetries that exist independent of human perception. Yet these objective mathematical properties are beautiful to human eyes and minds. This convergence of objective mathematics and subjective beauty is one of the most remarkable aspects of snowflakes. Snowflakes are a testament to the elegance of nature's design. The word design suggests an external designer, and snowflakes are not designed by anyone or anything external. Yet they are designed in the sense that they express principles and organization. They are designs created by physics and chemistry, by the laws of nature itself. In snowflakes, we see nature's creative power, the way that simple laws lead to beautiful, complex structures. The geometry of snowflakes is a beautiful example of nature's symmetry. Symmetry is one of the deepest principles in nature. It underlies physics, it underlies chemistry, it underlies biology. Snowflakes are a clear and visible expression of symmetry. When we study snowflakes, we are studying one of the most fundamental principles of nature itself. Snowflakes are a symphony of intricacy and beauty. This poetic description captures something true about the experience of observing snowflakes. Each snowflake is an individual, unique, yet part of a universal pattern. Billions of snowflakes fall from the sky, and each one is different, yet all share the same mathematical principles. This is a symphony, in the sense that it combines unity with diversity, order with infinite variation. Mathematical models help us understand snowflake formation. Science gives us tools to understand nature. Through mathematical models, we can simulate snowflake growth, can understand how temperature and humidity affect form, can predict the general characteristics of snowflakes that form under different conditions. These models reveal that the apparent randomness and diversity of snowflakes emerges from deterministic physical laws. This is the power of scientific understanding. Snowflakes are nature's exquisite mathematical masterpieces. With everything we have learned, we can appreciate the appropriateness of this description. Snowflakes are exquisite in their beauty, mathematical in their precision, masterpieces in the sense that they are examples of nature's highest creative achievement. In snowflakes, nature has created structures of remarkable beauty that are also expressions of deep mathematical and physical principles. Few things in nature combine beauty, complexity, and mathematical elegance as completely as snowflakes do. The symmetry of snowflakes is a direct result of the hexagonal lattice. As we come to the conclusion of our exploration, we return to this fundamental principle. Everything in snowflakes, from the largest visible symmetries to the smallest details, flows from the hexagonal lattice. The lattice is both the source and the expression of snowflake perfection. The variety of snowflake shapes is a result of changing environmental conditions. The diversity of snowflakes is not random or meaningless variation. It is a direct and understandable consequence of the variation in atmospheric conditions. Different conditions produce different forms. The snowflake is a faithful record of the conditions that created it. In studying snowflakes, we are studying the atmosphere. As we rest in the contemplation of snowflakes, let us appreciate what they teach us. They teach us that beauty and mathematics are not separate. They teach us that complexity emerges from simplicity. They teach us that individuality and universality can coexist. They teach us that nature expresses itself through geometric principles and mathematical laws. And they remind us that in the natural world, we live in the presence of extraordinary beauty and elegance, if only we pause to notice. The snowflake falls through the winter sky, a tiny masterpiece, carrying within it the record of its journey, expressing in crystalline form the principles that govern the natural world. Each snowflake is a meditation on geometry, a prayer in ice, a song sung in frozen water. As they accumulate on the ground, blanket the trees, and cover the earth, we are blessed with a reminder of nature's infinite creativity and mathematical precision. In snowflakes, we find both science and wonder, both reason and beauty. In the gentle descent of snowflakes, we find peace. Segment 15. The atmospheric journey and environmental choreography. Let us now deepen our exploration of the atmospheric journey that shapes each snowflake, understanding how the sky choreographs the dance of crystal growth. Snowflakes experience changing temperatures and humidity as they fall through the atmosphere. We have touched upon this before, but now let us linger in the contemplation of what this means. The atmosphere is not a uniform space. It is a dynamic, layered system with invisible boundaries between regions of different temperatures and humidity levels. As a snowflake begins its descent from the cloud where it was born, it enters this complex atmospheric landscape. With each meter of descent, conditions shift. With each moment of time, the environment evolves. The snowflake is not simply falling. It is navigating, responding, growing in relation to an environment that is constantly changing. The shape of a snowflake depends on temperature and humidity as it falls. These two variables are like the coordinates of an invisible map through which the snowflake travels. At any given moment in its descent, the snowflake occupies a specific temperature and humidity value. These values determine how the crystal grows in that moment. Move the snowflake to a slightly different altitude or a slightly different location, and the temperature and humidity change, and the growth patterns shift. The snowflake is like a sensitive instrument, measuring the properties of the atmosphere through its own growth. Each change in environment alters the crystal's growth pattern. Imagine the snowflake as having a kind of memory, a record of every change it has experienced. When the temperature drops suddenly, the growth pattern changes. When humidity increases, branching accelerates. When the snowflake passes from a dry layer to a humid layer, its growth mode shifts. These changes are not destructive. They do not erase the crystal's previous form. Rather, they are additive, building new structure on top of what came before. The snowflake accumulates these changes layer by layer, creating a visible record of the atmospheric variations it experienced. At temperatures around -22 degrees Celsius, snowflakes often form plate-like or columnar shapes. This specific temperature is significant. It represents a kind of threshold or transition point in the atmospheric temperature profile. Above this temperature and below it, different crystal forms predominate. At this particular temperature, the growth rates on different crystal faces reach a balance that favors the formation of plates and columns. This is neither too warm nor too cold, but precisely at the point where these forms are preferred. It is as if nature has drawn a line on a temperature scale and said, "Here, at this temperature, these forms will emerge." Above saturation, snowflakes grow more lacy and ornate. Below, they are more compact. Saturation is a measure of how much water vapor the air contains relative to how much it could hold at that temperature. When air is above saturation, meaning it contains more water vapor than it can hold, water is condensing. The snowflake finds itself in an environment rich with material to build from. It grows rapidly, eagerly, extending branches in all directions. The result is lacy, ornate structures with delicate, elaborate features. Below saturation, when water vapor is scarce, the snowflake cannot grow as rapidly. It must be more conservative with its growth, creating more compact, denser forms. Complex patterns like side planes, bullet rosettes, and planar types arise from changing conditions. Each of these forms tells a story of atmospheric transitions. A snowflake with side planes has developed flat extensions on the sides of its arms, indicating specific temperature and humidity conditions. A bullet rosette represents multiple crystals forming together or growing in a clustered arrangement. Planar types have various configurations of flat plates and surfaces. Each form is a message written in ice describing the conditions that created it. To a trained observer, reading a snowflake is like reading a weather report from the atmosphere through which it fell. If a snowflake starts as a column and then enters a plate-like regime, capped columns form. This transformation captures something essential about snowflake growth. The snowflake does not have a predetermined final form. Rather, its form emerges as a direct result of the conditions it encounters. A snowflake that experiences columnar growth conditions for a time, then transitions to plate-like conditions, develops a distinctive form that reflects this transition. The caps at the ends represent the moment when conditions changed, when the growth regime shifted. The snowflake is a visible timeline of changing atmospheric conditions. Snowflakes experience changing temperatures and humidity as they fall from the clouds toward the earth. This journey downward is a journey through invisible layers, each with its own characteristics. Some layers are warmer, some colder. Some are drier, some more humid. The snowflake passes through all of these layers sequentially, experiencing them in order. The order matters. A snowflake that encounters a cold, dry layer first, then a warm, humid layer, develops differently than a snowflake that encounters these layers in reverse order. The sequence of conditions is as important as the specific conditions themselves. The molecular lattice determines which surfaces grow slowly and which grow rapidly. At the molecular level, different crystal faces have different surface structures. Some faces have atomic arrangements that make it easy for new water molecules to attach. Other faces are oriented in ways that make attachment difficult. These differences in attachment ease, which flow from the molecular lattice structure, determine which faces grow fast and which grow slow. In turn, the relative growth rates determine which forms emerge. The entire process is rooted in molecular geometry, translated through growth rates into macroscopic crystal forms. Faceting reveals the geometry of the water molecule in large crystals. This principle deserves repeated contemplation. The geometry we see in a large snowflake is not something added by external forces or by the snowflake's encounter with the atmosphere. It is an intrinsic property of water, revealed and magnified through the crystallization process. The flat faces, the angular relationships, the proportions, all of these reflect what is built into the water molecule. The snowflake is like a telescope turned inward, magnifying and revealing the microscopic world of molecular geometry. As we contemplate the complexity of the atmospheric journey, we gain appreciation for the remarkable sensitivity of snowflakes. These tiny crystals are measuring instruments, responding to the finest variations in temperature and humidity. Each snowflake is a record, a document written in ice, describing the atmospheric conditions through which it fell. In studying snowflakes, we are studying the sky, reading the atmospheric conditions through the medium of crystalline form. Segment 16. Growth Dynamics and the Dance of Crystal Expansion. Let us now explore in greater depth the specific mechanisms by which snowflakes grow, the detailed dynamics of how water molecules accumulate and transform simple forms into complex structures. As snowflakes fall, they collect more water molecules and form branches. This process of continuous growth is at the heart of snowflake formation. The snowflake does not simply exist. It actively grows, accumulating mass as it falls. Each water molecule that condenses on the crystal's surface adds to its form. The accumulation of many molecules creates visible structures. The formation of branches happens as the crystal encounters conditions that favor branching growth. Branches extend outward from the surface, reaching into the surrounding air, seeking to capture more water molecules. In this way, the snowflake actively builds itself through its descent through the atmosphere. Branching is an unstable process that creates complex structures. The instability of branching is paradoxically what makes it creative. When a growing crystal surface becomes unstable, small perturbations amplify. A tiny bulge on the edge becomes a larger bump, which becomes a branch. This instability is not destructive. Instead, it is creative, generating the intricate structures that make snowflakes beautiful. Without this instability, without this sensitivity to small perturbations, snowflakes would be simple, regular blocks. The instability transforms simplicity into complexity. Higher humidity yields faster growth and more complex structures. When the air surrounding a snowflake is very humid, water vapor is abundant. The crystal can grow quickly, pulling in water molecules from its surroundings as fast as the water molecules can attach to the growing surface. This rapid growth creates conditions that favor branching, because rapid growth on different faces of the crystal can proceed at different rates. The competition between these rapid growth rates, combined with the instability of rapidly growing surfaces, creates elaborate branching structures. High humidity is the catalyst for complexity. The interplay of faceting and branching shapes snowflakes. These two processes are like two artists working on the same sculpture. Faceting creates smooth, ordered surfaces. Branching adds intricate details and elaborate features. When faceting dominates, the result is a simple, ordered crystal. When branching dominates, the result is an intricate, elaborate form. Most snowflakes experience some of both, creating a balance. The balance point determines the final form. A snowflake rich in faceted surfaces with just enough branching to add interest often achieves the greatest beauty. The knife edge instability is a third major force in snowflake formation. In addition to faceting and branching, there is a third mechanism at work. The knife edge instability operates at the edges of growing crystals. As a crystal edge grows, it can become unstable, developing ripples and perturbations. These perturbations can grow and develop into the delicate, lace-like features that characterize many snowflakes. The knife edge instability is particularly important in generating the finest details, the most delicate structures. It is the mechanism by which knife-sharp edges become decorative and delicate. Without this instability, snowflakes would be smaller and blockier. This observation reveals something important about nature. Stability is not always desirable. The universe does not require everything to be stable and unchanging. Some degree of instability, some sensitivity to perturbations can lead to greater beauty and complexity. The knife edge instability makes snowflakes possible. Without it, crystals would grow into simple shapes. With it, they grow into the elaborate, beautiful forms we admire. The basic geometry is a hexagonal prism, but variations abound. This statement encapsulates the relationship between universality and diversity in snowflakes. The hexagonal prism is the template, the universal form that all snowflakes begin with. But starting from this universal template, infinite variations are possible. The variations emerge as the basic prism is elaborated through growth in the varying atmosphere. A single template, infinite variations. This is nature's method of combining order with diversity. Elaborate structures develop as crystals grow larger. There is a clear relationship between size and elaborateness. A small snowflake has not had time to grow or space to elaborate. A large snowflake has had both time and opportunity to develop complex structures. A snowflake that falls a long distance through the atmosphere has more time to grow. A snowflake that encounters conditions that favor branching has the opportunity to develop elaborate branches. The largest, most elaborate snowflakes are those that have had both time and favorable conditions. They are monuments to a long and varied journey through the sky. Columnar crystals may become hollow or grow into thin needles. The fate of a columnar crystal depends on the conditions it encounters. In some cases, the interior becomes hollow, creating a delicate, thin-walled tube. In other cases, the crystal grows ever narrower, becoming a needle-like structure. These different outcomes reflect different growth conditions. A column that grows in a way that allows the interior to remain hollow develops one way. A column that grows more uniformly develops another way. The structure that emerges is determined by the specific growth conditions. the rates at which different surfaces grow, the duration and intensity of growth. Snow crystals can grow into a variety of forms depending on facet growth. The growth rate on each face is the key variable. Understand growth rates and you understand the diversity of snowflake forms. The relationship between growth rate and crystal form is not random. It is systematic and predictable. Given knowledge of temperature and humidity, scientists can predict the growth rates on different faces. Given growth rates, they can predict the crystal form that will develop. This predictability, embedded in physical laws, underlies the remarkable order and consistency in snowflake formation despite the apparent diversity. As we contemplate the growth dynamics of snowflakes, we gain appreciation for the delicate balance of forces that shape them. The snowflake is not passively formed, it actively grows, continuously expanding, continuously responding to its environment. The growth is governed by physical laws, but within those laws, there is room for variation and complexity. The snowflake grows according to nature's rules, yet each growth path is unique. This combination of law and variation, of order and diversity, creates the remarkable phenomena we observe in snowflakes. Segment 17. The scientific study and mathematical beauty of crystals. Let us now turn our attention to how science has come to understand snowflakes and how mathematical principles illuminate crystal formation. Snowflakes can be modeled using mathematical equations. This is a remarkable achievement of modern science. The complex beauty of snowflakes, the seemingly chaotic variation from one crystal to another, can be captured and described using mathematical models. These models incorporate the physics of crystal growth, the effects of temperature and humidity, the dynamics of water molecule attachment. By solving these equations, scientists can simulate snowflake growth. The simulations often produce results that closely resemble real snowflakes, capturing not just the general form, but often the specific details and intricate patterns. This demonstrates that the beauty of snowflakes is not mysterious or unexplainable. It emerges from physical principles that can be expressed mathematically. Mathematical models help us understand snowflake formation. The process of creating a mathematical model forces us to understand the underlying physics. To write equations that describe snowflake growth, we must first understand what factors influence growth. We must measure growth rates, understand how temperature affects them, understand how humidity affects them. We must understand the geometry of the crystal surfaces and how the shapes of those surfaces affect growth. In this process of model building, we develop deep understanding of snowflake formation. The model is not just a tool for prediction, it is a tool for understanding, a way of translating physical intuition into mathematical language. The Koch snowflake curve is a mathematical model inspired by snowflake patterns. Named after Danish mathematician Helge von Koch, the Koch snowflake is a fractal curve constructed by a simple iterative process. Start with an equilateral triangle. Replace each side with a bump, creating a more complex shape. Repeat this process infinitely, and you get the Koch snowflake. Though this mathematical object is different from real snowflakes, it captures something essential about them. It is fractal, meaning patterns repeat at different scales. It is infinitely complex, yet constructed from a simple rule. It demonstrates how simple rules can generate complex beauty, a principle that underlies real snowflakes as well. Fractals are pervasive in nature, and snowflakes are a prime example. A fractal is a geometric shape that exhibits self-similarity at multiple scales. Ferns are fractals, trees are fractals. River networks are fractals. Coastlines are fractals, and snowflakes are fractals. The self-similarity in snowflakes can be observed in the way branches resemble the whole, in the way secondary branches resemble primary branches, in the way the pattern repeats at smaller and smaller scales. This fractal nature is not accidental. It emerges from the growth process. The same branching rules that create large branches can create smaller branches at smaller scales. The result is a self-similar fractal structure. Snowflakes exemplify fractals, with patterns repeating at different scales. This self-similarity is one of the defining characteristics of snowflakes. Look at a snowflake at low magnification, and you see a pattern of 6 arms branching outward. Zoom in on one arm, and you see branches coming off that arm with a similar pattern. Zoom in further, and you see branches on those branches continuing the pattern. The pattern repeats at successively smaller scales. This is what makes snowflakes fractals. The fractal structure allows snowflakes to develop extraordinary complexity while remaining governed by simple rules. It is a principle of infinite complexity from finite rules. The mathematics of snowflakes involves geometry, symmetry, and group theory. These are the branches of mathematics that provide the language and tools for understanding snowflake structure. Geometry describes the shapes. Symmetry describes the invariances. Group theory is the formal mathematical language of symmetry. Together, these branches of mathematics provide a complete framework for understanding snowflake geometry. Every aspect of snowflake structure can be described in these mathematical terms. In this way, the snowflake becomes not just a physical object to be observed, but a mathematical object to be analyzed and understood. Geometry describes the shapes and arrangements of water molecules. At the molecular scale, water molecules are arranged in specific geometric patterns. The bonds between molecules form specific angles. The distances between molecules are specific. These geometric relationships determine how molecules can pack together, which arrangements are possible, which are most stable. At larger scales, this microscopic geometry is reflected and magnified in the geometry of the crystal. The large-scale geometry of the snowflake is literally an enlargement of the molecular geometry. Water molecules form hexagonal rings when they bond. The hexagonal ring is the fundamental building block of ice crystal geometry. 6 water molecules, each bonded to 2 others, form a ring with 6 sides. This ring has inherent hexagonal symmetry. The hexagonal symmetry of the ring is the source of the hexagonal symmetry of the crystal and ultimately of the snowflake. From this small hexagonal ring, magnified billions of times, emerges the familiar 6-pointed shape of snowflakes. Hexagonal rings stack in a hexagonal lattice, forming the basic unit of a snowflake. The rings do not remain isolated. They interact with other rings, bonding to them, stacking upon each other. The result is a 3-dimensional lattice structure. This lattice has hexagonal symmetry when viewed from above and certain three-dimensional symmetries when viewed from different angles. The lattice is the framework, the scaffolding upon which snowflake growth builds. Every snowflake, regardless of how elaborate its final form, is fundamentally built on this hexagonal lattice structure. Symmetry helps describe the invariance and patterns of snowflakes. Symmetry is a mathematical concept that describes invariance under transformations. A snowflake has six-fold rotational symmetry, meaning it looks the same when rotated by 60 degrees. It has reflection symmetry across multiple axes. These symmetries are not decorative. They are expressions of the physical laws that govern snowflake formation. The symmetries tell us something fundamental about the forces that shape the crystal. Understanding the symmetries is understanding the physics. The shape of snowflakes is determined by the properties of water molecules. This is the deepest principle. The shape is not arbitrary. It is not a matter of chance or accident. It is determined by the properties of water. Change the properties of water and snowflakes would be different. But water is water. Its properties are fixed. Therefore, snowflakes have the forms they have. The shape emerges necessarily from the properties of water. In this sense, every snowflake is an expression of the fundamental nature of water made visible and tangible. Segment 18. Rare forms, anomalies, and the exceptions that prove the rule. Let us now explore the fascinating exceptions to the normal rules of snowflake formation, the rare and anomalous forms that sometimes emerge under unusual circumstances. Occasionally, snowflakes form rare triangular crystals with only 3 sides. This is one of the most surprising facts about snowflakes. Given the fundamental six-fold symmetry inherent in water's molecular structure, one might think that threefold symmetry would be impossible. Yet it does occur, though rarely. These triangular crystals represent deviations from the normal hexagonal pattern. They remind us that while the hexagonal form is the lowest energy, most stable configuration, other forms can occasionally form under unusual conditions. These rare forms are not failures or mistakes. They are demonstrations of the flexibility and complexity of natural systems. Snowflakes can also display 12-fold symmetry, a multiple of 6. Some snowflakes exhibit 12-fold symmetry, which is 2 times 6-fold. This can occur when crystal growth creates a pattern that doubles the fundamental hexagonal symmetry. The result is a snowflake with 12-fold rotational symmetry, 12-fold rotational axes instead of 6. These snowflakes are unusual, yet perfectly consistent with the rules of crystal geometry. They demonstrate how fundamental symmetries can combine and create higher-order symmetries. 8-sided snowflakes are not possible due to water's molecular structure. While 6-fold and 12-fold symmetries are possible, 8-fold symmetry is impossible. This is not because 8 is an arbitrary number that water dislikes. It is because the angles between water molecules, the bonds that hold water molecules together, are incompatible with 8-fold symmetry. The mathematics of crystal lattices and the chemistry of water bonding together make 8-fold symmetry impossible. You will never find an 8-sided snowflake. The molecular structure of water forbids it. Plates can be simple hexagons, stellar with extended branches, or sectored with prominent ridges. The plate form of snowflake comes in several varieties. The simplest is a plain hexagonal plate, unadorned except for the basic hexagonal shape. More elaborate plates develop stellar features with arms extending from the sides of the hexagon. Still other plates develop sectoring with visible divisions and ridges creating a sectored appearance. Each variety represents different growth conditions, different balances between faceting and branching, different histories of temperature and humidity variation. Bullet rosettes are clusters of columnar crystals with a tapered look. Bullet rosettes are among the most distinctive snowflake forms. Instead of a single crystal, a bullet rosette consists of multiple columnar crystals arranged in a cluster. The individual columns are typically oriented at angles to each other, creating an overall form that resembles a cluster of bullets or a pointed shape. Bullet rosettes often form when multiple nucleation sites are present, or when columnar crystals grow together. They represent a different growth mode from the single crystal snowflakes we more commonly observe. Stellar plates sprout 6 primary branches, forming star-shaped crystals. The stellar snowflake is perhaps the most iconic form. Picture a flat hexagonal plate with 6 arms reaching outward. These arms are primary branches, extensions of the basic hexagonal geometry. From these primary branches, secondary and tertiary branches can emerge, creating an increasingly elaborate star-like structure. Stellar snowflakes can be remarkably beautiful, with the 6-fold symmetry creating a perfectly balanced form. They are often the most photographed snowflakes, the ones we think of when we imagine snowflakes. Fern-like dendritic structures can reach up to 10 millimeters in diameter. Dendritic snowflakes, named for their fern-like appearance, are among the largest snowflakes that form. With a main axis and many branches coming off at angles, they create a branching pattern that resembles a tree or a fern. These snowflakes can grow quite large, reaching sizes of several millimeters across. The delicate branching structure can be extraordinarily complex, with branches at multiple scales creating a fractal-like appearance. Capped columns are rare and exotic, with 2 plates on the ends of a column. Capped columns represent a specific type of growth history, a transition from columnar to plate-like growth. The snowflake begins as a simple columnar prism, growing vertically with the basal faces growing slowly and the prism faces growing more rapidly. Then the conditions change. The temperature or humidity shifts in such a way that plate-like growth becomes favorable. When this happens, the top and bottom of the column, the basal faces, suddenly begin to grow rapidly, forming flat hexagonal plates. The result is a column with plates capped on top and bottom, creating a distinctive and unusual form. Side branches are always separated by multiples of 60 degrees. Even when snowflakes develop unusual forms, even when they display anomalous symmetries, the angular relationships are always consistent. The angles at which branches extend from primary arms are always multiples of 60 degrees. This angular consistency reflects the underlying hexagonal geometry. No matter how complex the growth pattern becomes, the basic angular relationships are preserved. This is the way that order persists through complexity in snowflakes. Perfect symmetry is more the exception than the rule in snowflakes. This statement, which we have mentioned before, deserves careful consideration in the context of rare forms. Even the most beautiful snowflakes, those that appear to have perfect six-fold symmetry, often show subtle asymmetries upon close inspection. Perfect symmetry would require that the snowflake experience absolutely identical conditions on all six sides as it grows. Since the atmosphere is not perfectly uniform, and since local conditions around different arms vary, perfect symmetry is rare. Most snowflakes show some asymmetry, some variation between arms. This asymmetry is natural and expected. It does not diminish the beauty or mathematical elegance of the snowflake. Remnants of the original hexagonal prism shape are often visible at the center of larger crystals. No matter how large or elaborate a snowflake becomes, traces of its origin remain. At the center of the snowflake, you can often see the original hexagonal prism structure from which the entire crystal grew. This is like the core of a tree, a record of the earliest stage of growth. The elaborate structures, the branches and arms, grew outward from this central core. The original form was not erased. It remains visible at the center, a testament to the continuous development of the snowflake through its descent. Segment 19. The ultimate truth of snowflakes and nature's designs. Let us now approach the conclusion of our journey with deeper reflection on the ultimate significance of snowflakes and what they reveal about the nature of reality itself. The lowest energy structure for water molecules is a crystal with six-fold symmetry. This is not a preference, not a choice. It is an imperative, a necessity flowing from the laws of thermodynamics and quantum mechanics. When water molecules are given the opportunity to arrange themselves with minimum energy, they choose hexagonal symmetry. This choice is written into the molecular structure of water. The six-fold form is the natural, inevitable form that water assumes when frozen. In this sense, snowflakes do not become six-sided. They must be six-sided. The form is not imposed from outside, it emerges from within the nature of water itself. The formation of snowflakes is a complex process influenced by many factors. Yet this complexity emerges from simplicity. A few simple principles, applied through varying atmospheric conditions, generate the extraordinary diversity of snowflake forms. Temperature and humidity vary the growth rates. Branching and faceting compete. The knife-edge instability creates delicate features. From these simple elements, complexity emerges. This is one of the most profound lessons snowflakes teach us about nature. Nature is economical. It achieves tremendous complexity through the application of simple principles in varying circumstances. The beauty of snowflakes is a result of their symmetry and geometry. Why are snowflakes beautiful? Because they are symmetric, because they are geometric, because they express mathematical principles in visible form. The beauty is objective, rooted in the mathematical and geometric properties of the crystals. Yet it is also subjective, perceived by human minds and appreciated by human sensibilities. This convergence of objective mathematical beauty with subjective human perception is mysterious and profound. It suggests that mathematics and beauty are deeply connected, that the human capacity to perceive beauty reflects an underlying order in nature. Snowflakes are a testament to the elegance of nature's design. The word design implies an external designer, yet snowflakes are not designed by anyone. They are self-organizing, emerging from the interaction of water molecules with their environment. yet they are beautiful and elegant, as if they were carefully designed. This paradox reveals something important. Nature does not require an external designer to create beauty and elegance. Order and beauty emerge naturally when simple elements interact according to natural laws. Snowflakes are not exceptions to this principle. They are exemplars of it, clear demonstrations of how order and beauty emerge from physical laws. The geometry of snowflakes is a result of the molecular structure of water. We return again to this fundamental principle, for it is so essential to understanding snowflakes. The geometry is not added to the water from outside. It emerges from the water's own nature. The six-fold symmetry is intrinsic to water. The branching patterns are potential in water's molecular structure. The stunning beauty of snowflakes is the beauty of water revealing itself, expressing what is inherent in its chemical nature. In every snowflake, we see water's true form, the form that water naturally assumes when given the opportunity. The six-fold symmetry is a direct result of the hexagonal lattice. The lattice is the foundation. The symmetry is a direct consequence of the lattice structure. Change the lattice and the symmetry changes. Preserve the lattice and the symmetry is preserved. This logical necessity, this direct causal relationship between lattice and symmetry, reveals the deep order in snowflakes. Nothing is arbitrary. Everything follows from the lattice. The lattice determines the symmetry. The symmetry determines the large-scale form. The laws of physics and chemistry are inexorable, determining outcomes with precision. The hexagonal lattice is the key to snowflake symmetry. The lattice is more than just a structural feature. It is the key, the unlocking principle that reveals snowflake nature. Understanding the lattice is understanding snowflakes. The lattice explains the six-fold symmetry. It explains why three-fold symmetry is rare. It explains why eight-fold symmetry is impossible. The lattice is the organizing principle, the fundamental truth underlying all snowflake variation and diversity. The arms of a snowflake grow independently from the corners of the hexagon. This independence is crucial. It is what allows variation and individuality within the hexagonal framework. Each arm is not a slave to some central authority. Each grows in response to its own local conditions. Yet all are constrained to grow from the corners of the hexagon, maintaining the overall structure. This balance between local independence and global structure, this combination of freedom and constraint, creates the snowflake's remarkable character. The snowflake is individual yet bound to universal principles, unique yet part of a universal pattern. The unique conditions for each snowflake ensure no two are alike. This famous statement, which we have explored throughout our journey, finds its deepest meaning here. The uniqueness of snowflakes is not mysterious or miraculous. It is a simple consequence of the complexity of the atmosphere. The atmosphere is chaotic. Small differences in initial conditions lead to large differences in outcomes. Given the number of snowflakes and the number of possible atmospheric paths, the probability of two snowflakes being identical is essentially zero. Every snowflake is unique because it has experienced unique conditions. The uniqueness is guaranteed by the nature of the system. The molecular structure of water ensures that all snowflakes have 6 sides. This absolute constraint, this inviolable rule, reveals something important. Not everything varies. Some things are fixed. the six-sided nature of snowflakes is not variable. It is not subject to environmental conditions or random chance. It is fixed by water's molecular structure. This fixity, this unvarying core, provides the foundation upon which all the variation and diversity is built. The variation is possible because there is a fixed foundation. The six-fold geometry is the constant, and everything else varies around it. Snowflakes are nature's exquisite mathematical masterpieces. We can now fully appreciate this designation. Snowflakes are exquisite because they are beautiful beyond ordinary expectation. They are mathematical because they express mathematical principles with precision. They are masterpieces because they represent the achievement of nature's creative power. They are the result of simple physical laws applied through varying atmospheric conditions, generating structures of extraordinary complexity and beauty. In snowflakes, we see nature at its finest, creating beauty and order through the expression of its fundamental laws. Segment 20. Final reflections on snowflakes and the infinite winter. Let us now arrive at the final segment of our long journey into snowflakes, bringing together the strands of understanding we have woven throughout this exploration. Every snowflake begins as a tiny hexagonal prism shaped by water's molecular structure. This is where we began, and it is where we return at the beginning. Every snowflake's journey starts with this simple form. This tiny prism is the seed, the germ, the beginning point. From this simple form, all complexity emerges. The elaborate stellar snowflakes, the delicate dendritic crystals, the rare triangular forms, the exotic bullet rosettes, all begin as tiny hexagonal prisms. This humble beginning, magnified billions of times through the crystal growing process, reveals the elegance and order of nature. The six-fold symmetry of snowflakes arises from the hexagonal lattice of ice. This is the repeating principle that we have encountered throughout our exploration. The lattice creates the symmetry creates the form creates the beauty. The chain of causation is clear and necessary. There is no randomness in this process. There is only the inevitable expression of water's nature through geometric form. Each snowflake's arms grow independently from the corners of the hexagon. This principle, stated at the beginning of our journey, remains true and important at the end. The independence of growth, combined with the constraint of hexagonal geometry, creates the remarkable combination of unity and diversity we see in snowflakes. Each snowflake is an individual, yet all are members of a universal family. This is a lesson that extends beyond snowflakes, teaching us about nature's way of combining order and variation, universality and individuality. No two snowflakes are exactly alike due to unique atmospheric conditions. This statement, which we have explored from many angles, represents the democratization of uniqueness. In snowflakes, we see that uniqueness is not rare or special. It is universal. Every snowflake is unique. This is not because snowflakes are special or chosen. It is because of the complexity and variability of the atmosphere. Each snowflake has experienced a unique journey through a unique atmospheric path. Therefore, each snowflake is unique. This universal uniqueness is a beautiful principle. It tells us that in nature, variety is not the exception, but the rule. The molecular structure of water ensures that all snowflakes have 6 sides. We return to this principle repeatedly because it is so fundamental. The constraint is absolute. Water cannot create snowflakes with other numbers of sides. The molecular structure forbids it. This inviolability reveals the deep order in nature. Physics and chemistry are not arbitrary or negotiable. They are built into the very fabric of reality. Snowflakes must be six-sided because of this deep order. The order is not negotiable. Snowflakes can display six-fold rotational symmetry, meaning they look the same every 60 degrees. This symmetry is not accidental or approximate. It is exact, following from the geometry of the hexagonal lattice. When rotated by 60 degrees, every feature should return to its original position. In perfect snowflakes, this symmetry is exact. In snowflakes with some asymmetry, the symmetry is approximate, but the underlying principle remains. The six-fold symmetry is the default, the natural form that snowflakes assume. Asymmetries are deviations from this natural state, interesting deviations that record the unique atmospheric conditions. Reflection symmetry allows a snowflake to look the same when flipped over three axes. We have mentioned this symmetry before, but it deserves final contemplation. The snowflake has mirror image qualities built into its structure. Not just one mirror plane, but three. This threefold reflection symmetry, combined with six-fold rotational symmetry, creates a structure that is mathematically complete and balanced. The snowflake is not just rotationally symmetric, it is also reflectively symmetric. It is symmetric in multiple ways, creating a structure of remarkable balance and elegance. The shape of a snowflake depends on temperature and humidity as it falls. This principle governs the diversity of snowflakes. While the six-fold geometry is fixed, the elaboration of that geometry is variable. Temperature and humidity determine how the basic hexagonal form is elaborated. They determine whether the crystal becomes columnar or plate-like. They determine whether branches develop. They determine the size and complexity of the final form. In this way, the fixed geometry is combined with variable elaboration to create tremendous diversity within a universal framework. Above saturation, snowflakes grow more lacy and ornate. Below, they are more compact. This relationship between environmental condition and crystal form is consistent and predictable. Above saturation, where water vapor is abundant, growth is rapid and complex. Below saturation, where water vapor is scarce, growth is constrained and simple. This relationship demonstrates that snowflake form is not arbitrary or random. It follows physical laws. Given the temperature and humidity, we can predict the general form the snowflake will take. This predictability reveals the order underlying snowflake formation. Complex patterns like side planes, bullet rosettes, and planar types arise from changing conditions. The variety of forms is real and remarkable, yet each form corresponds to specific atmospheric conditions. This correspondence between conditions and form reveals that snowflakes are not creating themselves randomly. They are responding to their environment. Each form is a message, a record of the atmospheric conditions the snowflake experienced. To those who know how to read it, a snowflake tells the story of its creation. As we conclude our long journey into snowflakes, let us reflect on what we have learned. We have learned that the snowflake is not a simple object. It is a complex result of the interaction between fundamental physical laws, environmental conditions, and the specific journey each crystal takes through the sky. We have learned that beauty and mathematics are intimately connected, that the beauty we perceive in snowflakes reflects underlying mathematical order. We have learned that snowflakes are individual yet universal, unique yet bound by unchanging principles. In snowflakes, we see nature's infinite creativity working within constraints. The constraint is the hexagonal geometry fixed by the molecular structure of water. Within this constraint, infinite variations are possible. No two snowflakes are identical. The combination of fixed constraint and infinite possibility creates a system of remarkable elegance. This is nature's way. This is how the universe creates beauty and diversity from simple principles. As winter snows fall, as billions of snowflakes descend from the clouds, each one carries within it the order and beauty we have explored. Each one is unique. Each one is perfect in its own way. Each one is a testament to the elegance of nature's laws. In the snowflake, we find a mirror of the universe itself, reflecting mathematical order, physical law, and infinite creativity. In the gentle fall of snow, we find peace, we find beauty, we find home. May this journey into snowflakes bring you rest and contemplation. May the image of these perfect crystals, unique yet bound by universal law, settle your mind and calm your spirit. In the silence of falling snow, in the infinite descent of snowflakes from sky to earth, we find a rhythm that echoes the rhythm of nature itself. This is the snowflake's gift to us, this reminder that we live in a universe of order and beauty, mathematical precision and infinite creativity. May you rest well in this knowledge, knowing that every snowflake that falls carries with it the elegance of nature, the poetry of physics, the grace of existence itself.